Hello, welcome back to another episode of the Reliability Gang podcast. I'm here with my right-hand man, Will Crane. How we keeping, buddy?
Doing very well, thank you.
How's your week been, mate?
Busy.
We've both been on our side quests again. I feel like I don't really speak. Oh, we do speak in audio, but I feel like we're so full on what we're doing, and we come Friday, and it's just like
we're just very focused on making sure we're delivering our service to their customers.
Like even our little catch up is not a little catch up, is it? It's like literally 15-minute about the whole week, and I'm like, oh, and then I do mine and all the rest of it. But I mean, yeah, it's been great because I feel like you're more on the reliability quest, really helping people with the reliability stuff and really formalising the roadmap for certain customers. And I've kind of been on more of an electrical kind of quest with shaft current and motor current signature analysis, teaming up with Mark Gurney. And I thought, do you know what? Great podcast to talk about that journey today.
Yeah.
Because for me, just thinking about it has been a bit of a whirlwind.
And it's coming up more and more in conversation in the reliability chats I'm having with customers, which is, well, what about... Are we thinking about the electrical testing side of things? Like we've got all this mechanical stuff, we've got the VA, we've got the oil analysis, but what else can we be doing on some of the motors? We actually had one at one of the customers I was at this week, which they had a stirrer that stopped working. They went to change the motor. Got a bit of an issue there with problem solving. They changed the motor and didn't realise that the gearbox was also broken. But they changed the motor and it still didn't work. And then they've changed the gearbox and we're doing the RCA on that. But interestingly, this motor, when we got to it, although the gearbox had failed, the motor, we couldn't turn the shaft at all.
Really? Okay.
Absolute bound up. So me and the reliability engineer on site, we actually split the motor, right? And the motor had gotten so hot that the VPI resin had melted.
Oh, wow.
Right, to the point where it left like white residue all round the between the stator and the rotor.
Do you know what that white residue is? So it's the insulation papers that you get usually insulation class. It's like a plastic.
Right.
And when that gets, it's rated to quite high temperature stuff.
Okay.
But when it does get to that particular temperature, when it dries again, it
was like white ash.
It's like glue,
and it was like white glue, but it was so bad we couldn't get the rotor out.
Wow.
We literally, I'm sledgehammering the rotor out.
We've had that before as well when we've been in workshops, that things have obviously motors burnt out, the windings burnt out, and it's got that bad.
Yeah.
But again, this is also another kind of discussion as well, because when we do look at most failure modes in any plant and whenever we're doing anything, we're always looking at vibration as the number one. I get why, because it is a great indicator of many failure modes in one, isn't it?
Yep.
But one thing that we really don't do, especially with the bigger motors and different sides, is look at kind of the failure modes of the actual electrical side of it, because it is a very inherent failure mode. Like, well, when we do, for me, because on these particular kind of assets, which we have done this year, and we've been working quite close with quite a big manufacturer, and they're really looking to be able to really get the top end of reliability. They've been on a journey for a while. They've got a few sites in the UK, but they're all at different stages as well, which is quite interesting. But one of the particular sites has very robust CMS systems, a lot of information going in there. The maintenance system is being driven to drive out the PMs, and the guys are really kind of on top of a lot of things. They've got good condition-based maintenance in there, but they're now looking to improve them. Because I feel like when you've got all of that, you get to a bit of a ceiling.
Yep. And you're like, what next? How do we improve?
How do we now get above this ceiling? And if you don't really do some real sound for me, and understand the next level of where the failure modes are almost hidden when you're overlooking them, you're not going to be able to really improve from that point.
And I feel like this topic of how do we measure the electrical condition of our motors and manage them better has become more and more of a hot topic as people are becoming more and more aware of the potential damages from inverters.
Yeah, mate, drives as well. Like, the revolution of inverters in terms of where we are in the industry was crazy, because obviously technology it moves fast. And obviously back in the day, when you get some of these old plants, DC motors were the thing. That was the way that you control speed, and that was the way you did
all belts and pulleys.
All belts or pulleys in different ratios. And, you know, what we had to do back in the past is actually over-manufacture to be able to vary speed. You know, DCs are very difficult to overhaul. I've done a few DCs in my time, not much, but even when I was winding in the workshop, to do it interpole winding or field winding, it's kind of different. Interpoles were bar wound. But being able to do that properly took a lot of time. So the time it took for me to rewind the AC motor the whole thing, say for example, a 4-pole 15 kilowatt motor, we could probably do that in 4 hours. Do you know what I mean? That's from start to finish as a rewind. Okay, quite quick to be able to do that. You could probably do that within the day. Okay, that's still going to cost the customer quite a lot for that rewind, because you've got the parts, you've got the materials, and the copper, and all them other things that associated with it. An interpole or a field winding, you've got 4 in each winding for a DC, a field or interpole. And if you want to do a bar wound interpole, you're talking 2 or 3 days to get that really good. And that's just one interpole. So when you had a full rewind for a DC, you could be taking up to a week to do that properly. And that's a long time to be able to do so over the equivalent of an AC motor. So obviously the introduction to these drives was revolutionary, because what we could do now is start to actually say, well, we can start to replace some of these DC motors out for motors. The spares is a lot cheaper. It's a lot less risky to the business if something should fail. And it was a lot easier as well to test as well. Like an AC motor is a lot easier to test than a DC motor in terms of the winders, because you've got one winder in an AC motor, and then you've got different types. You've got a commutator bar as well with a DC. Loads of different little fading modes in terms of the electrical side of a DC. So yeah, I can see why the revolution was so...
And the energy efficiency was huge.
Massively.
That was a massive drive, even just for drives that were on standard motors that were just needed a slower speed, or even some motors that they were like, oh, well, we're having to run that at full speed, but we don't actually need full speed. We'll put it on inverter, save massively on energy
as well, and all the rest of it. So the need for them, inherent, massive. You know, technology did take that leap forward. But one thing that we miss within this whole scenario was understanding how inverters affect, shaft current, how they affect the winding, not just the bearings, and how also real simple ways of grounding can mitigate these from the get-go, from a design point of view. But again, this thing is what we've studied has been so misinterpreted by the whole industry. We were coming across this quite a while back, and my first shaft kind of current fluid journey started even my old company, right? And we found some electrical fluid on a compressor. We've got that customer now, but we've had any issues with that since. But when I first saw that, it was the first time I ever see it, and that was a good 8-9 years ago. So this shaft coil has been around forever, ever since drives have existed. But the problem is, what we've not done is understand what is really causing it, what damage it does not only just to the bearing, what other implications does it have further on down as well. And that's something that we've learned this year. And also, what are the mitigations around it? What are the other things at design stage need to be done correctly to be able to actually, eliminate the defect altogether, or the root cause of it? And unfortunately, I'd say 90% of the drives that we've got within the whole industry, that design bit hasn't been done.
No, because even on our journey at the beginning, we started off with the idea of the fact that, okay, we've got this shaft current. I don't think we really understood how it was necessarily being generated, but we knew it was in the rotor, and we knew it was discharging through the bearing. And the main kind of products on the market then to solve this problem was grounding rings, grounding brushes, different solutions that were being applied to the shaft, and that's what we were looking at doing.
Yeah, I mean, I think because when we first...
Sorry, no, to add on to that, but now thinking about it, even when we were doing that, we still were saying at that point in time was we still wanted to be able to measure this somehow. Yeah. And I remember we having so many conversations and buying lots of kits and scope meters around it.
We were, because I remember the first journey we had, we was measuring the voltage off the shaft. That was the way to measure, because what we didn't like to do is just put something on randomly and assume that the problem's been solved. We're vibration analysis engineers. We live our life on data.
We wanted to see the good or the bad, and then it good.
That's it. That's what we wanted to do. But the thing is, because of our lack of knowledge in that particular subject, and also the industry's lack of knowledge, it wasn't just ours. Because what was we doing when we was finding the problems? Right, we're going to go online. We're going to research.
Look into it.
So what we found was a lot of the shaft, ground, and current companies were selling devices that only warranted their product to prove that that product was doing something.
Yeah.
So when we look at business drivers for companies now, we've always got to look at a business driver now. We always got to do that. What is that business there to do? What is their outcome, and what do they want to push, and what do they want to sell, and what does that actually correlate to their business driver? And a lot of these things that, again, that we come across, especially nowadays, is to sell a product. That's what they want to do. That's how they make their money.
Which is a solution, and we have learned since then, which you'll come on to a bit later with Mark, is that they have somewhat of a place, but there's a lot of extra things that can be done first.
Exactly. And I think as well, it's always looking at root cause, or we do root cause analysis, right? Whenever we find a problem, what do we want to do? We want to go far as back as we possibly can to say, what is the actual root cause of this issue? We do it in reliability. We do a lot of it in vibration analysis. And again, vibration has detected these problems, and we've found fluting, and we, through our journey, have tried to go back.
How do we fix the root?
How do we fix it? How do we go back to the actual root cause of the issue? We know it's generated from the inverter, but also what mitigations do we do from that point that also allow us to be able to be far back as possible to that and try to mitigate that so it doesn't cause any further damage. And again, Mark Gurney is a huge, he's basically mentoring me now. Basically, that is my mentor when it comes down to electrical side of condition monitoring, because again, you need these people in the industry that have done their own extensive research, but also really understand the principles beyond the level of just selling a product. And that's why I've got a big markup here, really massively, because we just even had a conversation yesterday, and he's been on the podcast. We've been on the podcast. Then when he came in February, that's when we did the training. Okay, we understood that we didn't understand this to the level that we needed.
And even on my journey with the reliability piece, when I first met Mark at the Mobius conference in Manchester, and he delivered his presentation, I can remember everyone in the room was like, "Okay, whoa, yeah." Because for the first time ever, I felt that everyone in that room really started to understand, and everything Mark was saying made sense.
Yeah, he converted it to make sense, didn't he?
And he did it. He took a very complex topic and he made it simple to understand. And that's also when we then, as we were doing more of the ARP and we had more awareness with Mark, was just how big of an influence Mark's had in the reliability space as well, with the work he's done with Jason at Mobius, is that he is a massive mentor to us now at maintaining what we're trying to do. But what he is doing is he's leading the way in electrical motor management.
But we need a leader in that sense, because the thing is, this problem is becoming bigger and bigger because the more drives are introduced without the sound testing and the acceptance testing as well. That's another thing as well that
on new motors.
New motors, but new drives. Yeah, as well, like we got to be testing how much shaft current is actually coming off the drive to begin with before we even connect it up. Because when you connect that drive up and it's producing too much shaft current, you're causing damage straight away.
Yeah.
So this is the thing about reliability. It's about trying to, at that design stage, be able to mitigate as many of the failure modes as possible.
And I feel like from the conversations and the training that we have had with Mark, obviously you'll go into all the testing and how we do that, but a lot of the common mode and circulating currents are literally avoided from good design and installation.
Massively, yeah.
And I was even thinking now while we're talking about it, if you get that bit right, a lot of the potential damages can be avoided. You don't need to put a grounding device on necessarily, and in some instances that can make it worse. And I even thought my reliability brain's going at the same time, which is, when we do install a grounding brush, and this goes back to the customer where we first experienced this, if we do install a grounding brush or a ring, what we actually are now doing is we're introducing another failure mode that needs to be captured within the Formica.
The ring.
Because that ring might break. And what happened at the customer that we went to?
We did, and then that happened. What we did initially was put an Aegis ring on, working perfectly fine to begin with.
Sweet.
Right, so it was diverting the current away from the bearings. Unfortunately, because the shaft current was high, there would have been attacking and winding as well, but we didn't really know about that. We had no awareness of that. So that has obviously taken a bit of a hit from that. Has it failed because of that? No. But has it reduced the life expectancy of that winding? Possibly. But the problem was with that is that when they were lubricating that motor on the drive end, they were over-lubricating it. And the Aegis ring, how it works, is loads of tiny little carbon brushes around the shaft as a circumference. But as soon as you get any grease, dirt, dust, and let's be honest, most of the environments that we operate in are at least dusty,
And this particular motor was a little bit interesting in that it was the winding is completely open, isn't it?
It
pulled through the winding rather than just the cooling is pulled through the winding rather than go over the top of the external.
It's got an internal fan. So what it does, it draws air through, and it's also got open end shields to be able to cool the motor down. Yep. Obviously, great for cooling, but very poor for dust and grit. I don't know who designed that. Because surely having all of that dust, because when we opened that motor up as well, we had to spend a lot of time just trying to get
lots of compressed air.
Because we changed the bearing on that. And I remember that job. It's one of our first jobs that me and you did together.
It was.
And it was so fun. What a job. When we lined it, purred in it, we were just like, what a win. I went home that day very, very proud of what we did. But to this day, that's running. Still running nice. But again, though, this is another discussion. We know there's shaft current now. We're now revisiting going back to actually test the inverter source to see if we can now put some EMF coils on as well. So
what, obviously, from what we've learned from Mark is we know that there's a lot of mitigation that can be done at design and installation stage, and we'll probably go into that. But what are some of the things that we now can do or should be doing to manage our motors better? What are some of the tests that we now can do?
So in terms of that design stage, one of the first things that we do see a huge issue with, and I think the way that we can mitigate the quickest action to be able to start to reduce this problem massively is just how a motor's earthed correctly. How many motors have you seen with the earthing point on the frame completely unattached?
Loads.
Not even earthed. Loads. And also the mitigation of understanding, is the cable actually screen cable? Is it actually inverter rated cable that's being utilised and used?
On the earthing one, what tests could people do to try and find out if it's working properly?
So simple tests. So what Mark advised us to buy was a current clamp meter. Okay, so what that clamp meter does, it can test the impedance, resistance, and also have a look how much current is flowing through the PE, the conductor.
Right.
So all we're doing is basically putting a clamp over the actual
the main earth into the terminal block.
Main earth into the terminal block, and as well, what we should have on that particular motor is earth from the frame to a sufficient earth as well. But also, again, though, we have to then consider if that's earth to the frame, is that frame earth correctly as well? Because you got a fan.
You've got to make sure the chain is perfect.
The chain is perfect to earth. But remember as well, a lot of things are earthed as a final point of call to the actual frame. But if the frame is then on anti-vibes, which are rubber, to the floor,
it's not then.
You haven't even got a good earth. So the idea is how can we lower that path of resistance from the actual source of the inverter to earth as a lower path of resistance
as quick as
possible? Because we can put a shaft grounding ring on if we want to, and we might be able to actually ground the rotor. But if we can't dissipate the actual
it can't get anywhere
to earth quickly, it's going to recirculate again some way, or going to cause damage or travel to another.
And this is where
actually
a grounding device can cause more damage, right?
Yeah, 100%. So if you've not really earthed your actual motor correctly, right, and you've got a shaft device on that particular,
it might travel to the driven machine.
It will actually start to try to find a lower path, but that generally can be through a compressor or a pump. Or gearbox. And people don't understand that this shaft current can travel. I think it's hard for people to get their head around. And it was for me at first, because the problem is we're mechanical engineers. I mean, I was actually electrically trained, but then I went into vibration analysis. So it was like I understood the principles, but I was quite lucky that I also was a winder. I understood three-phase theory, I understood how things were wound, I understood this. So also when Mark was telling me that the shaft current that appears can really attack the first turn within your winding. Like really bad on startup. And
that's because of, we talked about this in the track, this is because of reflective voltages within that first court turn.
So what a lot of winding manufacturers do now is on inverter driven motors is put another layer of insulation around that first turn. But if that winding has been rewound and it hasn't followed that practice, which is quite common.
So if you don't tell your rewind company or they're not experienced or whatever.
Exactly. They're not going to do that, because when they obviously spec a winding to rewind it, what they do essentially is count the pitch and count the coils from the top. When they spec it out, they'll cut the head off, burn the motor around, pull the coils out. But once you burn it off, you're not going to be able to see that insulation on that first turn anyway. So again, even winding shops has a responsibility to understand, are we copy winding this to the actual specifications? Or you can have a motor that's been installed that's not inverter driven
before, then they've rewound it to be.
Or they've changed, like, for example, that one we was at the other week. This motor is not designed to be run on inverter, but they've then changed it to inverter. Obviously, that nameplate is not going to say it's inverter duty.
So if it goes away.
Exactly. But this is the thing as well, is getting the context around every element. Like, how many times have we seen a spare motor with a roller bearing be put in as a You know what I mean? Like a spare in there, same motor, but it's designed for a bell-driven application, thrown into a straight coupled application. It's not got the right bearing for the application. We see it all the time in industry.
So that earth clamp that we spoke about earlier, that's obviously a really good measure to see whether or not you've got any current going back down to the earth.
Measuring the earth leakage.
So we on that main earth coming out of the terminal block, you are expecting to see that going back.
100%.
And if it's not, that's a concern.
That's a concern. And then what we can do is as well, what we've seen sometimes is just from where the frame is to another suitable earth point, we measure it. And if it's very low, the current, we know that there's some form of issue. And sometimes it's literally the case of taking that earth off, cleaning the surface.
And then you can see it.
And then putting it back on to see a difference.
And that's what Mark did his last conference in Barcelona, was that shaft current can be as simple as scraping a bit of paint away.
Do you know, Mark's a huge advocate for it. It is, because he generally says, do you know how many problems and issues just come from that first simple way of earthing a motor? And obviously the thing is, though, you can't just go do it without testing. Does that make sense? So you can't just go, I'm going to chuck earth on here, chuck earth on here. We've also got to use that current clamp to test to see if what we're doing is making a difference, and using data from it as well.
You also mentioned earlier about how important the cable selection is for an inverter-driven application as well.
Yeah.
What's about that?
So inverter-driven cable, this is something that Mark's taught us as well, is very important, because what you get is something called screening on that cable. Okay. So when we've got that inverter drive, what we do is we get EMF kind of dissipate through the cable as well. And that, if you've not got screen cable, can actually jump to other lines and cause shaft current in different areas. Yeah. So Mark was telling us that one time with one of the scenarios they had basically changed a similar scenario to the one that we've just dealt with. They both were normal direct online motors, and they changed one of them to an inverter for efficiency reasons. They didn't change the cable though, all right? But what was happening was, because the cable wasn't screened, the shaft current was traveling down both lines, affecting the bearing on one of them, but it was also affecting the bearing on the sister motor, because both cable runs were coming from the same panel and they were run side by side.
And they were charging the other line.
It was. So what the screen cable does, it protects it, and it doesn't allow it to also jump, if that makes sense, and it keeps it contained. Okay?
And I remember Mark saying as well, unusually, unlike other maybe electrical grounding, with inverters, you have to screen both ends.
Both ends, exactly. So what you get on a lot of applications is when that screened kind of cable runs from one end of the inverter to the other, what we want to be able to see is that screen part, all that mesh, earth correctly at the inverter end. Yeah. Good earth, but also on the other end where it goes to the terminal block, really well earthed. But the problem with that is as well, what we've seen is that some terminal blocks have gaskets. Yeah. So if you've earthed it even sufficiently at the gasket, well, if it isn't earthed correctly from that terminal block to earth, then it's going to try to travel back up.
And I suppose that's why on some really big motors, they have the earth cables between the actual terminal block and the frame of the motor.
They have that. You've seen that as well on most applications.
Well, I remember Mark mentioning this a little bit as well, and you start to build the picture so much more about this. Well, what about the gland that goes into the terminal block? Isn't there special glands as well?
Yeah, so them glands obviously clamp all the way around that screen. Yeah. Okay? If that's a plastic gland, well, that ain't going to be earthing, is it? And we've seen inverted duty cable and with a plastic gland. It's like, this is the whole point of this is completely pointless now. Yeah. But also what you can get is these lugs that come off that gland. You've seen them little lugs?
Yep.
How many times have you seen them just drilled into the terminal blocks? Yeah. The whole reason for that is to be able to take a lower path again to Earth. Right. So we should be seeing another cable from that to the Earth point. Okay. Yeah. And that way we also can measure the leakage there as well. And
we've got a new tool from SKF as well that does a lot. What is that?
Right. So the TechEd. Okay. So the SKF TechEd tool. This is a really great non-intrusive tool to be able to measure them EMF generated from the inverter on the cables or whatever. It's a non-contact probe, and what it does, it measures very high frequency counts, basically where that shaft current is coming, because that shaft current is extremely high frequency. Okay, this is why it's very difficult to see it within our spectra as well, because we're only measuring to a certain frequency range. We can see some inverter frequencies, but the damage is coming from the harmonics of these frequencies, not the actual frequency themselves. So when we're looking at harmonics of that high frequency noise, I mean, we've often seen sometimes our loop factor reading that we've got within our spectra is roughly about 600,000 to 900,000 cycles per minute, we've seen initial inverter frequencies within that range sometimes, right? But what we're looking at is the harmonics of that particular frequency, which we can't even see. Ultrasound, high frequency ultrasound can detect this as well, okay, which is quite interesting. But again, when we're looking at an oscilloscope, which we'll get onto in a minute, we are really looking at the source signal, but that sample's extremely high frequency. I think they're megahertz, some of these oscilloscopes. The one that we've got, that Mark got us to get, is megahertz. The frequency is a bit, it's happening so fast, it's really difficult to wrap your head around.
And in vibration, we're just dealing most of the time in kilohertz.
Yeah, exactly. So when you're talking megahertz, it's a whole, and it's really hard for me to even think how quick that's happening. Does that make sense? Because when you look at electronics and how quick things happen, it's a different world to what we're dealing with mechanical vibration analysis and the frequencies that we're looking with. So yeah, the TechEd's a really great tool to be able to just see non-intrusively when
you can use that along the cable and near that gland that we were then talking about.
So we can use it along the cable, we can have a look how, vicious it is and how many counts we're getting. And generally, what the settings on it does, and it's not a kind of trendable measurement, if I'm honest, it's more of a just
an indication.
But what I do is set it to maybe 10 or 30 seconds, and then I can almost not trend, but maybe have a look at the severity across a certain amount of motors. So what we'll do is set the TechEd to 30-second count, see how many counts it rises to over 30 seconds, and then we can kind of gauge a severity through that as well. And we're already starting to gauge what's good and what's bad ourselves from our own data that we're bringing in. So what's really good is to see that from the cable, have a look at what's coming off the cable, and you will get some coming off the cable depending if it's screen cable or not. But what we are looking for is it traveling through the motor? So the non-drive end going across the whole circumference of the motor, seeing if the counts are high, and going across the drive end. And if you're seeing counts at your motor, you're very, very likely to be having very poor shaft current.
And that really then instigates really going delving in deeper now, which is why we have the scope meter and the Rogowski coils.
So important, because even what we've found, we might have high shaft current come from the inverter, but the good earths might be taking the majority of that away, right? We want to try to reduce that anyway because it's best practice to. But the problem is as well, just because you've got no counts being measured doesn't mean that your bearings are not getting damaged.
And from all these tests so far, we've obviously got some indication that shaft current is happening, but there is two kind of types of shaft current, right, that we can detect, and it's the scope meter that helps us see what type they are and what we need to do to fix them, because it's not just grounding, is it? There's another type in which people may be more familiar with the insulated bearing, right?
Yeah, circulation. So circulation current. So it's really difficult for us to know what type is there if we don't actually have a look at the source with the scope.
Right.
So the scope will do two things. It will measure basically a voltage, a peak-to-peak voltage, because it's looking at a sine wave. It's looking at the line frequency coming in, okay? But what we're going to be able to do, a bit like vibration analysis, is be able to look at the patterns that you've got from that sine wave and what you've got, okay? So a good example of it, if we're seeing a really clean sine wave with no spikes coming off it, we know that actual signal is pretty clean in terms of the way it is.
In terms of the common mode, but the circulating is quite high, isn't it, if it's got the sine wave?
Yes.
If you're around all three phases, that is, because it should be, the idea, I think, when Mark said, is that it should be flatline because they should all just balance out to zero, right?
Yeah. So circulated currents will show if you're seeing a more of a sine wave.
Yeah.
Shaft current, common mode current come from the inverter. That essentially
the spiky
bits, the very high frequency harmonics of.
If you're watching this on a video, hopefully I might be able to
pull a few.
Go on, you can put a few.
We've got a few. We've got a lot of data now actually, where you get these little spikes coming out, of the signal. They're common mode currents, and they're the harmonic frequencies of them inverter frequencies, and they're the ones as well that will cause your peak to peak to be higher, because just like you've got in a time waveform, if you've got low RMS values but high peak to peak values, your crest factor will be high. So it's almost like crest factor to a degree, and the higher these peaks are coming out,
the more significant.
Exactly, but that is going to give you a higher peak to peak count, but that also is going to correlate to a lot more current, because what we're looking at shaft current, we're not measuring voltage, because the Rogowski coil is looking at current.
Yeah.
But a
Which
Rogowski,
is plugged into the scope meter.
which is plugged into the scope meter. So we get a voltage read off of the scope meter, and we convert it to current through an equation of what the Rogowski coil's set to.
Yep.
And we set it to 1 amp to every I think every 1 volt is 0.33 of an amp.
Gotcha.
Okay, so then we can do that calculation, and then generally what we're looking for as a measure, we really want under 10 amps in terms of shaft current coming off that inverter. That's a safe zone. Anything over that is considered too much and potentially can cause damage.
Yeah.
With a lot of drives will be over that, because all the drives that we've tested, generally most of them
Are above.
Which is crazy. It's mad to think of. But what we're now doing is, regardless of whether that's causing issues down the road, we're still trying to reduce it, because an EMF core will reduce that.
So I was going to say, so in terms of, obviously, that sine wave is an indication that we've got circulating currents, and that is for an insulated or an insucote bearing, can help mitigate that, to break that path.
Because the problem is, what we've seen, everyone's like, it's insulated bearing, it's still got fluting. It's because, remember, insulated bearing is only going to really cover you for your circulation currents.
And what I've understood from Mark is that obviously that insulated bearing is for that sine wave circulating current. That spikiness is down from the inverter and the shaft current, but that will peck away at that insulation on that bearing.
Yeah.
And once it goes,
first
time of the winding, and once that goes, actually the circulating current is more damaging, and it takes it out so much quicker.
Because you've broken the insulation from that one particular earth path from the non-driving of the bearing.
Yeah. So you talked about those EMF cores. So what are they doing?
So the EMF cores is all new to me. Like, these also have been actually in some designs of some inverters for like, one of the customers that we were talking to would get sent these EMF cores with the inverter, and they'd just say, "What's this?" Just
Oh, really?
They didn't know what it did. They didn't know what it did. It was one of these things,
and they just chucked them.
Yeah. So some drives have been like designed to be able to have these mitigated, or not all drives, but some drives have these in this particular occasion. But what they're there to do is actually reduce the amount of this shaft spikiness and smooth out the signal with a coil.
Yep.
So basically, what it does is like an inductance. It takes that high frequency, it stores it in the actual coil itself. The coil heats up a little bit, and it prevents it from moving any further from that point, if that makes sense.
It's a little bit like, I don't think it's an exact thing, but when I was looking into it, it's like, when you sometimes get data transfer cables and they have that lug on magnetic.
Exactly.
It's a little bit like that.
That's the same.
Yeah, I think it is the same concept.
Because, you can get that and you can take that off as well. And then
so
get away.
That shaft current and spikiness and those EMF cores, that's going to kind of try and smooth that out a little bit. That's the idea with those.
That's the idea. What we're trying to do is take that damaging kind of current that really will attack your bearing and the insulation away, and then mitigate that at source. And the good thing is, what we can do is we can test with a Rogowski coil afterwards. Before and after.
Oh, okay, that's
so we can then see what
it smooths it out.
Yeah, and also what we'll do is take when that coil gets a little bit hot, we know it's working. So we can use thermal imaging as well to be able to make sure.
Should that then be, do these need to be inspected as a check, just to make sure they're not getting too hot?
What I'd say is we're in line with your thermal imaging surveys, is to make sure that
at the same time.
Yeah, and maybe even trend it, has it got too hot? If it's getting too hot, is that getting affected? But I do also believe you should still do shaft current tests on these as a condition modeling
to make sure it's all
because what we can do is, and we'll get onto motor current signature analysis as well, which is a really good way to measure certain running attributes of your motor, is that you can still take an MCSA test with a Rogowski coil and you can do them tests together. Do you know what I mean?
So
one after the other.
This spikiness that we're seeing in the inverter, are some inverters worse than others?
Yeah, all different. And
so brand that you buy.
Brands are, but you could have two identical inverters, the same brand, and they could be emitting the completely different shaft currents.
Really? Okay.
I've tested it. I've had it, and I'm still on my journey. Right, I'm in test phase. I'm in experience phase. I'm I'm having a look, going across these different sites, and I've tested a lot of inverters now already, even within a short space of 3 months. And I'm starting to see patterns of what we've got, and I'm also starting to see the different waveform patterns as well. But also, what we can also see from that, which I spoke to Mark about. That waveform was talking about, we had one where it was more of a triangle wave. Okay. So Mark was like, well, we've definitely got an issue here with potential issue with the rotor, because it should be sinusoidal and it's more of a triangle.
Yeah.
So then now the different patterns can now point to different failures of the actual motor or the rotor itself.
And I suppose this factors into now one of the things that Mark's had a lot of support with, and it is definitely becoming more and more. It was always a topic that we spoke about in vibration analysis. It was always, okay, how do we do electrical motor testing? But it's definitely become a lot more pioneered, especially with the motor doc, with Howard Penrose and what he's doing on LinkedIn, and he'll be sharing a lot of things. Him and Mark have been in communication quite a lot.
Yeah.
But this is motor current signature analysis now, and it's becoming a lot more as a tool, isn't it?
I think this is the future, personally. And I think it's really difficult for people to get their head around, if I'm honest, because I think vibration analysis at first, even when you explain that to people, is black magic.
Yeah.
But when you start to go into electrical signature and you start to say we can start detecting different faults and different things.
And bearing defects.
And bearing defects. The problem is it's really hard for people to get their head around mechanical faults to be detected electrically.
Yeah.
And it is difficult because, your subconscious belief system doesn't...
No, they don't relate.
don't mix. But again, you've got to be open-minded in this game. And I do think that there's a huge place for MCSA in the future. We've now teamed up with Mark as well. We've got a motor dock on the way.
Yep.
We've got AT.
I think for people who are trying to understand the difference, so vibration analysis is using a vibration transducer to measure that acceleration value through a piezoelectric crystal. Motor current signature analysis is using the variability of the air gap and that current to generate that same sine wave of a frequency, and a spectrum is generated, isn't it, within the motor dock?
Yeah, so it's FFT that is generated from the electrical signal, opposed to FFTs can generate from any signal, right? So we can get a spectrum out of that particular signal. But the beautiful thing of getting a spectrum out of that particular signal is that you can measure now the actual damage of your rotor bars, because the higher the sidebands you get through that electrical signal will give you a really clear indication whether you've got issues with your rotor bar. It's really difficult to do that from an oscilloscope perspective. It's a bit like trying to detect faults in your time waveform with vibration analysis. It's really difficult to do because you just got lots of different signals playing together. But what MCSA is now doing is being used as a spectral analysis, but also because it can measure that frequency and that air gap, it can also measure certain elements like vibration analysis can,
like a bearing defect.
With like a bearing defect, because it can still identify them fault frequencies as a frequency, as an event that's happening through that variable air gap. Because remember as well how high it can actually measure and how quick it can sample.
Is it a lot more high frequency in sampling in MCSA compared to VA?
Yeah, massively.
Yeah.
So this is why it also can take a real high number of different failure modes, and it's incredible what we can get out of it. And I don't understand it fully yet, but for some of the things I'm researching into, and obviously speaking to Mark and following Howard's kind of research, there's still a lot more to learn with it. But now, non-intrusively, you can start to detect a lot of issues. So, say for example, you've got submersible pumps.
Doesn't matter.
Say now you've got a borehole pump.
Yeah.
Say you've got assets that are so hard to reach. And if we can start to mitigate these failures just as effectively as we can vibration analysis and detect the electrical frequency faults, potentially the winding, the rotor.
Yep.
Who tests their rotors nowadays?
And what interests me as well, I was talking about this with the customer the other day, is that, we're talking about with this particular customer about IoT and how things are moving forward, and AI and the limitations, and technology is moving so quickly right now. But one of the limitations that we have with vibration analysis and IoT is you've got sensors all dotted around the factory, gateways all over the place communicating. Well, if MCSA becomes a place where it is as good as, or gives enough of an indication of a problem of a bearing on a motor, or even, and in some cases I've seen in the motor dock, we're measuring vane pass rates and blade pass and gear mesh frequencies as well.
Not even that.
Belts.
It can let you know. I mean, Mark was on the phone to me the other day.
Yeah.
They did a test, and it could say that the belts were too tight. And you tell me how VA is going to do that. There's certain failure modes that we struggle with VA.
Yeah.
And I'm trying to get my head around that. I was like, how has it done that? And again, it's just another level of understanding, because there is science behind it. And when you go deep enough into the science, it does make sense.
So you think, though, if this does become a very important technology in the future, and the world is moving towards AI and acquiring data, well, it's a lot easier to acquire motor current signature analysis data from the MCC, from the electrical cabinet. You don't have to have nodes across the whole factory. It's all done in the motor control center. Exactly. It doesn't have to be done out on the motor.
Exactly. I mean, you consider we've got a customer now looking to be able to go to that 4.0, and what we're doing at the moment, we have to consider all options of vibration and motor current signature analysis together. But imagine now you don't have to cable run
everywhere or gateways all over the factory. It's all done in the MCC.
Of course, like for me, obviously that motor air gap measure is in the motor. Like my testing that we're going to do is see how effective it can go further.
Yeah, how far?
That for me, okay, I admit the motor, I'm quite confident it can do it. But I think one thing, I'm trying to get my head around whether this is right or wrong. I don't want to make any statements because I've not done any tests. But what I think MCSA can do very well is identify there's a problem. But what I think vibration analysis is really good at is severity. And that is really key, especially with really... So the way I see the future happening, like vibration analysis is not too expensive to do now. It's getting cheaper and cheaper. I do see these things probably going in line.
Complementing
each other as well. Depending on...
As with anything that we do in condition-based maintenance, don't rely on one technology.
No, and again, we've done Famicas on certain assets. And this has completely changed the way that we're actually doing condition monitoring, because condition monitoring shouldn't just be vibration analysis. Condition monitoring is monitoring the condition of the winding, the rotor, the other elements that potentially could fail to cause that asset to fail. Doesn't mean we do it every month, but like we should be doing motor current signature analysis to check if the rotor's okay every 6 months. As a minimum, we should be doing shaft current testing every 6 months. Because say, for example, even you've put an EMF core, or maybe it's not working anymore, and if you're going to mitigate failure, it's not difficult to do them checks on your very critical assets twice a year.
And with a good maintenance strategy, with the right PMs in place so that you're not wasting your time and you're being effective within your team, you can upskill, you can get the training. Mark can come with us. We can bring the tools and equipment to be able to do this. Or if you haven't got the resources or experience,
we can do it.
We can help with it.
And that's what we're doing now. So when we're doing Famicas, what we're doing is identifying, well, the rotor is a part of that asset. How are you demonstrating that the rotor is in good condition? Because if you're just doing an insulation resistance test, you're only testing the winding, but that's also not good enough for the winding.
Yeah.
Like we're not testing the rotor. You've got a whole moving part there that's really intrinsic to that whole function. And we're not even testing it. We don't even know the condition. So this is where motor current signature analysis is so important. It is a driver to be able to test that rotor, but also it now has a full host of other things it can do.
And all of this ultimately boils down to the criticality of the machine.
Yeah,
if this tiny little conveyor, we're not going to worry about
all that. But what we're doing, though, is the AA assets, the really important ones.
Cat ones.
Crit
ones even.
Yeah, and we want to be able to say, have we extended the life of that motor from maybe 5 years, 10 years to 30, 40? And if you mitigate that shaft current, if you ensure that you're doing the right test electrically, you reduce it a massive amount. You ensure the bearings are lubricated sufficiently and on condition and done
with the best polyureas.
Yeah, ones that don't bleed, and you can do that. And you can make sure that mower is good. We can extend the life of these assets for a very, very long time. Problem is, we've got so used to
dealing with failure,
accepting failure, accepting the fact that these things, that's lasted 10 years. That's done great. It's like, well, what was it supposed to do? 30. Well, is that great? No, it's not, is it? If you look at that, it does not even reach its expected L10 life. And the problem is we're accepting failure way too much. We've got to change our expectation of what failure means. And that means we do need to do these tests. We do need to understand what's important. We need to go to the end of the earth to understand the failure modes. And then also, when we've done the Famicas, we've got to put a maintenance plan in place that covers them. How many times have a company's done Famicas? But also, when we do them, we've got an extra layer of knowledge, right? So when we've understood that, okay, you've got a motor and the rotor could fail or the winding can, we can't just say, just do a mega test, just do an insulation resistance test, because doesn't actually cover the winding, because even that winding alone has different ways it can fail. Phase to phase, turn to turn. You've got all these other failure modes, even in the winding game. Like when I was winding, we'd get winding in, and there'll be a different fault for each winding in the pattern. So you see, for example, one winding with just the phase burnt out. Well, that's an overload of the phase. You'll get one winding where you'll get turn to turn faults, right? You'll get one winding where the whole thing's burnt out as an overload. So there's different fault conditions for the winding. But the main common one that we found was turn-to-turn failures, right? And a mega insulation resistance test, if you're testing between phases or to earth, doesn't even cover that one failure mode. So a lot of people that are doing this test,
They think they're just mega in.
they think, the motor's absolutely fine. Your insulation resistance test is no way near good enough to actually ascertain whether that wind is in good condition. And you've got a static test. So we invested in the ADX tester at first.
Which we use in the workshop.
But again, surge testing is a good way to understand whether there's any turn-to-turn faults, but you are inducing a voltage into the winding. Personally, if you're doing that in a workshop environment, I think that's fine, because if it fails, it fails.
You deal with it.
It's not good enough anyway. You don't want that going back out, and you need to rewind that motor. Simple as that, okay? But if you're doing that in the field
and it fails,
great, you found the failure, but great, now we've got an issue, right? We've got a problem. Because you potentially, if you've
stressed the winding,
you stressed it too much, are the company in a good enough position to have a spare or whatever on a very large motor? I think it's too risky. So we've now bought an AllTest Pro tester, which allows us to test the turn-to-turn faults through frequency rather than energizing the winding.
Gotcha.
Okay? So now that one failure mode of turn-to-turn shorts, which is a very common failure mode with windings, we can test and we can trend.
Yep.
And now we'll have a database with all of these assets, the electrical test, the resistances, the impedances, the resistances to earth. We can still do insulation resistance, but we can also do that frequency test. That allows us to check for them turn-to-turn failures.
Yeah.
So now when we do them comprehensive tests, we can say confidently
that's okay.
That motor winding is okay, right? And as soon as we see any deviation from that, we see a trend drop or whatever.
So we can trend with the AllTest.
We can trend it. We trend them just like we would vibration analysis. We trend it. You need to trend. You need to have a baseline. We need to know when it's started to come out of tolerance. Because if it is, we can then plan.
Yeah.
Right, we need to get a new motor in. And look, let's be honest, who wants to be keeping a 300 kilowatt, 500 kilowatt, 690 kilowatt motor spare?
You don't want to have it sitting there. It's deteriorating.
Yeah, it's expensive. It deteriorates. But I understand why people still carry it, because there's a fear. But the thing is, if we can be so confident in what we're doing,
our detectability,
with our detectability, right, we can mitigate the risk. We don't need to have all them spares sitting on the shelf.
Yeah.
But then we can act at really early. But it does need consistent testing and good condition-based maintenance.
Good discipline.
Discipline as well. And just saying, oh, well, that's been, and this is another argument. Oh, it's been fine for 5 years. We don't need to test it anymore. It's like, this is the most insane thing I've ever heard, because defects can occur randomly. And that's what we test for.
All it needs is to have a bit of load vibration, and then the winding gets loose in there. And
then you get something happen. And if you just say, okay, we're going to do it once every 2 years, then again, it's a bit like vibration. Oh, we'll do it once every year or once every 3 months. Then you're risking the risk. But I'll be honest, these tests don't cost a lot of money to do from the criticality of the assets. Do you know what I mean? A company like us can set up a plan for it. We can say, look, this is how often it needs to be done. We can write it into your PMs, and we can make sure.
And close it off.
And that's what we're going to do for a major company. We're looking at all of their electrical tests on their critical motors. But when you look at everything across the whole business, each particular site, there's not a huge amount, because we're only doing it on
the big players,
the big critical assets, and the ones that have a criticality RPN score, and where we can reduce it with this particular technology. So this is where we need to go. It's not just vibration analysis is going to mitigate this now. If we really want to be reliable, we need to look at our electrical systems.
Managing our electrical motors effectively.
Exactly. Because I think a lot of people have kind of probably not mastered vibration, but a lot of people are doing it now.
They understand the mechanical side of things, and there are a lot of people that have that good mechanical knowledge, but there's less people with the detailed electrical knowledge that Mark's been able to bring to the table with this.
Yeah.
And it is becoming more and more important, and I hope that for anyone listening to this has been able to come away and may rethink their maintenance strategy, or look at their Famicas, go, oh, I didn't consider that. And that is why we do this podcast. That is why
awareness, isn't it? Because I'll be honest,
we didn't have the full awareness.
Like this year, my knowledge, like, you get areas within this, you know, you're following the same strategy and all the rest of it, and you learn a lot. But the last year, how much I've learned with this electrical side, it's all coming full circle though.
Yeah.
Because I used to be a winder, and so all of these things make sense now. I'm like, that's why we see that often. And now I'm coming back with this new knowledge. It's almost getting reinforced what I knew before.
Yeah.
But also now as you can see, I'm quite amped up and excited about this. I'm getting quite passionate about this, because
I hadn't noticed.
Oh, sorry. Sorry, I calm myself down. But like, now's the time to act. We are too slow off the mark. We're too slow. Like, everyone's talking AI. We want to do this. We want to do that. If we're not gathering data right now, good data, sound data, doesn't matter about AI. You're never going to make it work.
But you think for the big companies, with the companies that have got these really important assets, where's the value? AI or doing good motor testing?
Exactly. Where's the value? What are we doing now to make sure we're doing what we should be? What's the outcome of what our actions are doing? It's got to be always driven. How do we make that asset live longer? That's got to be the number one talking point. Because the minute all we're doing is just saying, when's it going to fail? That's not good enough. That is not what we need in this industry. If we want UK manufacturing to be here and be healthy, be strong, and be sustainable, we've got to be thinking, how do we make these assets live longer? Because if we can make them assets more reliable,
it's more sustainable.
So sustainable. We are so wasteful by just, even if we detect things, we're replacing, and the lines are still running. But also not even that. Motor current signature analysis can see how efficient we're running our motors.
Yeah, that one really interests me because
interesting.
With the motor dock, what we're able to do is it can tell how much that motor is costing to run. We can laser align it and we can see the cost difference afterwards, which inherently has been quite challenging to measure that.
It has been. And I think there's some equations that we've been from Aquam or whatever, but you want the proof in the pudding. You want that as a return on investment. Because how are you ever going to gain trust to say, we need to align all of your motors across the site? They're just not going to be bothered by it if they don't know what the impact's going to be and if it's going to be big enough for them to do.
Yeah.
But I guarantee you're right. If we did that on 2, we can model that. And then you can say, well, if we did this across your whole plant, this is how much energy you're going to save. Energy prices are probably only going to go up.
Yeah.
We're living in hard times right now. Like, I think a lot of people forget the cost of living and everything we're going through. Like, inflation's massive. It's huge. The cost of parts is huge.
Lead times
is huge. Now, companies now are they're forced to look into reliability.
And I think that's why the reliability has taken off so much, but they're having to do something.
Because I'm not being funny. Back in the day, when energy prices were next to nothing, parts were easy to access. Do you know what I mean? Plants could afford to run unreliably and still make a lot of profit. Do you know what I mean?
Whereas they didn't have to worry about the lead times, did they? Whereas it's like, what do you mean that one tiny part is going to be 12 weeks?
I need to make sure this asset's reliable. And again, the end goal should always try to be making the assets reliable because there's so many hidden benefits like sustainability and the cost of things. And if you do that across the world, then it does make a huge impact to the way that we live. But again, the problem is what is a lot of business drivers driven on? It is cost and it is money, it is profit. I get there's all these other sustainability things and goals and stuff around the company. But I'll be honest, the number one driver generally in the business driver is to be able to, how do we make as much product as possible and how do we sell it for as much as we possibly can? But remember, that is directly balanced out by good reliability. Because if you don't do that, then you're not going to achieve your goals anyway. And I think...
And on that note,
it's a good way to end it. So guys, thanks for tuning in. I'm going to just now sit down for it.